All right, this is Unit 1 and AP Stat still. This is Chapter 6. This is the last chapter of the unit. So we kind of went over and hit over a lot of this stuff when we did our last overview with Chapter 5. I kind of sprinkled it all in there, but I want to make sure that we get some more recap with this, and I'll go over some more practice problems with this so we can kind of see everything and summarize it. But in Chapter 6, we're talking about the standard deviation as a rule. Right, we're using that and the normal model, using normal distribution even with the calculators and things like that. So the standard deviation as a rule, the trick is comparing very different looking values, is to use standard deviation. All right, we can kind of make them all kind of look the same. We were elaborating before. The standard deviation tells us how the whole collection of values varies. So it's a natural ruler in a way, scaling everything down to compare the individual groups of stuff. And as the most common measure of variation, the standard deviation plays a crucial role in how our data looks. And we've been discussing this throughout this whole chapter. Basically trying to say, when doing this, that median and interquartile range go together, but again, mean and standard deviation, we want to kind of make them go together. So we kind of standardize things with something called the z-score. We hit on this, and it's when you can compare individual data values to their mean relative to their standard deviation using this formula, right? And I used x's, the book is using y's, whatever. It's the sample mean and some sample value divided by the standard deviation. And we call the resulting values the standardized values, all right, standardized values as denoted as z, and they're also called the z-score is how it's referred to. It kind of makes everything standard in the same basic form where your mean is going to in turn end up being 0 and everything else is going to be a distance somewhere close to that, in the negative direction, like -1, 2, -3, or +1, 2, and 3, around in there. We standardize the values. They don't have units, all right, and z-score measures the distance of each data value from the mean, all right, so how far it is from the mean. That is one standard deviation. A negative z-score tells us that the data value is below the mean, while a positive z-score tells us that the data value is above the mean. And again, I went over a lot of this. This is just a review and the recap to kind of make sure that we were all paying attention, that we're still all on board with all of this. The benefits of this. Standardized values have been converted from their original units to a standard statistical unit of standard deviation of the mean. Makes things a little easier for us to find the variation then. And thus we can compare values that are measured on different scales, which is huge, different units, different populations. It makes everything easier for us to grasp and compare. If you're talking about comparing, like they always use that old adage, you're comparing apples and oranges. Well, if we compare them in the same light with the same unit of measure or the same z-score, then we could actually compare them together. So shifting data is the next step. We can either add a constant amount to each value, just add or subtract the same constant to the mean by just adding value if it's to the same amount. We discussed this one before, but this is another key item that they're going to hit on, and I want to make sure that you see it. This is true for the median and other measures of position too, by adding them to it. In general, adding a constant to every data value adds the same constant to measures of center and percentiles, but leaves measures of spread, which would be like standard deviation. Sorry about that, but leaves measures unchanged, so like your standard deviation, things like that. The following histogram show a shift from men's actual weights to kilograms above recommended weights. Right, so you're looking at number of the weight of men, and there's a box plot there, a number of men in kilograms, right? So you're looking at this, and you're kind of like, okay, they are basically about the same, right? So it says, the following histogram shows a shift from men's actual weights to kilograms. Nothing should change. I just altered what the value is. It's kilograms or it's weight, right? But because you're changing the values, the idea is it's just rescaling it. So it's rescaling data. When we divide or multiply all the data values by a constant value, All measures of position, such as the mean, median, percentiles, and measures of spread, as the range, interquartile range, standard deviation, are divided or multiplied as well. That's why in this example, it's the same, because to convert from certain weights, everything stays the same. Okay, everything will stay the same if I'm just changing it from like pounds to kilograms, for example, right? Just changing what that happens to be, whatever that weight happens to be, or multiply or whatever by a certain amount. The men's weight data set measures weights in kilograms, and if we want to think about these weights in pounds, we would have to rescale it, right? So now here's what I'm doing. I changed it, right? This was in kilograms, and notice that it's still the same, but it's in pounds now. So all I had to do is take everything that I had before, right? Everything that I had before, and now I am just multiplying it by something or dividing it by something, okay? So, back to some z-scores. Oh, sorry. But with this, just to make sure you understand, notice that the pattern is the same with these. Everything is just kind of pushed. And yeah, it might be a little more spikes here and there depending on what happened, but I just multiplied to change from pounds to kilograms. Whereas the last example, it was also the same shape, but I just moved everything up is all that happened. So the key, though, for you to remember is if you multiply every item by something, you change everything. From the range, from the standard deviation, from the mean, the median. But when you're adding, you're only changing the mean and median when you're adding to everything. That's the key that I want you to take away from this. Back to z-scores. Standardizing data into z-scores shifts the data by subtracting the mean and rescales the values by dividing their standard deviation. Standardizing data into z-scores shifts the data by subtracting the mean and rescales the value by dividing. So it's kind of doing both ideas in one, is what's happening if you think about it. Standardizing into z-scores does not change the shape of the distribution. Standardizing into z-scores changes our center by making the mean 0. Standardizing into z-scores changes the spread also by making the standard deviation 1. Is basically what's happening with this. So when is a z-score big? A z-score gives us an indication of how unusual a value is because it tells us how far it is from that mean, right? A data value that sits right at the mean has a z-score basically of 0. A z-score of 1 means the data value is 1 standard deviation above the mean, and if it's -1, it is 1 standard deviation below the mean. When a z-score is big, right, how far from 0 does the z-score have to be interesting or unusual? There is no universal standard, but the larger a z-score is, the more unusual it is, basically. The farther it goes out, negative or positive, the more unusual it is. And remember that a negative z-score tells us that the data below, or value below the mean, remember that a negative z-score tells us that the data value is below the mean, while a positive tells us that it is above the mean. When is a z-score big? There is no universal standard for z-scores. All right, there's no universal standard, but there is a model that shows up that we'll all see, and that is the normal model that we will use probably throughout the rest of this course, more than likely. And it's like a bell-shaped curve is what we try to get everything to model, that normal model. Normal models are appropriate for distributions whose shapes are unimodal and roughly symmetric. All right, so when they have one lump unimodal and they are roughly symmetric. These distributions provide a measure of how extreme a z-score is. All right, majority of our stuff is happening closer to the inside, and as it tapers off towards the ends, there isn't as much there. When is a z-score big? All right, there is a normal model for every possible combination of mean and standard deviations, right? The normal model consists of the population mean and the population standard deviation to represent that normal model, with that being said right there. And we use those Greek letters, which we went over before. That's the mean and that's the standard deviation, and they are part of that model. They don't come from the data. They are numbers that we choose to help specify the model, and such numbers are called our parameters. Parameters deal with the population. Notice I'm talking about the population, the parameters. We hit on these ideas before. All right, and that's why I keep spiraling back to what we're talking about here. Okay, summaries of data like the sample mean and standard deviation, they're just written with these Latin or Greek letters. All right, such summaries of data are called statistics, summaries of data or samples. Okay, and that's why depending on who's going over what and how you explain it and which books you're using, that's why I try to go over an overview and then I try to show it to you again, how even the book is showing it to you. And when we standardize normal data, we still call those z-scores, regardless if we're talking about a sample in statistics or whether I'm talking about population in terms of parameters. This is the same deal, right? This is a z-score for a population, and what I showed you before was for a sample. That's all. But you still do the same stuff. Once we have standardized, we need only one model. That model is basically saying, hey, the normal model, we're looking at the population or the sample mean as 0 and standard deviation as 1. This is the standard normal model or the standard normal distribution is what you're looking at. Okay? Be careful. Don't use the normal model for just any data set, since standardizing data does not change the shape. I can't just use this for any idea. We'll get to how we can kind of fudge some of this later on in the course, but for the time being, I can't just make up whatever I want and always make it work like this. When we use the normal model, we are assuming the distribution is normal. That's why you're doing it. Okay, we cannot check this assumption in practice, so we check the following conditions. Nearly normal conditions. The shape of the data's distribution is unimodal and symmetric. We want to make sure that's happening. This condition can be checked with a histogram or a normal probability plot. You kind of want to see what the graph looks like. Does it look normal or not? And I'll explain a normal probability plot later. I actually like them a lot. It's very helpful to see if they are or not. And if so, we can go over this rule, which we already hit on, and I'll pause there, and we can go over it when we come back.